Okay, so we're going to use the slope of our position graph to find the velocity, and then we're going to translate that down onto the velocity graph. Okay, so as long as we have a straight line of constant slope, we know the velocity is going to be the same. So where I just highlighted in pink, we know the velocity is going to be the same there. It changes kind of gradually, but starting from 10 seconds all the way to 18 seconds, it will again be at a constant velocity, and from 20 to 25 seconds, it will once again be at a constant velocity. So basically what I want to do is find the slope of the lines of the three different highlighted colors. Okay, so between 0 and 8 seconds, we've gone from a position of 0 to 12. So if we do velocity is rise over run, 12 is our rise, 8 is the run, and our velocity is 1.5 meters per second. Okay. Basically, we're going to go down to the velocity graph, and between 0 and 8 seconds, we just have a straight line at 1.5. It's at 1.5 the whole time, it never changes. Okay, so if you got that as your velocity, you're going to give yourself 1 point on part A of problem 1. Okay, the second constant velocity segment, I guess I need to move the camera so you can see it. Just by looking at this flat line, we should know that the velocity is equal to 0. There is no slope. Okay, what that means is on our position graph, between 10 and 18 seconds, our velocity is a straight line across at 0. Okay, and once again, if you got this segment, this is worth 1 point. Now right here, between 20 and 25 seconds, we start out at a height of 12, and we drop down to 0, so we have negative 12 divided by the run is from 20 to 25, that's 5 seconds, and negative 12 divided by 25 should give us roughly negative 2.1 meters per second. Okay, so we go down here, find 20 seconds, find something that looks like it's around 2.1. Okay, again, if you got something like this, give yourself 1 point. Okay, now the tricky parts are these sections. So right here it's kind of curved, right here it's kind of curved. That means we have some acceleration. But we just basically want to connect these two lines, and we want to connect it in a way that is continuous. Okay, obviously our velocity hasn't jumped way up to 4 meters per second or way down to negative 3 meters per second. So I'm just going to go ahead and draw a line between these two slopes. Okay, so your final graph should look like something like this, and if you connected your three individual segments, give yourself 1 more point. Okay, so that was part A. Now if you flip over to part B, the first part of part B says calculate the average acceleration for a time period t equals 8 seconds to t equals 10 seconds. Okay, so what we know is that average acceleration is equal to the change in velocity divided by the change in time. Okay, so if we flip back to our graph, we care about this segment right here between 8 and 10 seconds. At the beginning, since we made these lovely calculations, we know that we were going 1.5 meters per second. Okay, that was our initial velocity, and our final velocity is this blue line. We're traveling at v equals 0 meters per second. And the time elapsed, 8 to 10 seconds, is 2 seconds. So, change in velocity is final minus initial. Okay, our change in time is 2 seconds. Our final was 0 seconds minus 1.5 divided by 2. So our average acceleration is negative 0.75 meters per second squared. Okay, so that was part 1 of B. If you got that correct, then you should give yourself 1 more point. Okay. The second part of part B was asking you to draw a vector representing the direction of average acceleration. Okay, we have an average acceleration of negative 0.75 meters per second. Since our acceleration is negative, we know it must be pointing downwards. So all they're really asking you to do is draw a little downward arrow indicating that the acceleration was negative. Okay, and if you got that, give yourself 2 points. Okay, so again, part A was worth 4 points in total, part B is worth 3 points in total. Okay. On part C, it says, I'm going to move out so you can see it. Suppose there's a passenger of mass 70 kilograms on the elevator. Calculate the apparent weight of the passenger at t equals 4 seconds. So when something says apparent weight, what they're really asking for is the normal force. Okay, if you think back to the exercise we did with a penguin that was in the elevator, and I asked you all those questions about whether the scale would go up or down. So a scale reading in an elevator is basically an indicator of the normal force. So if you see apparent weight, they're just asking for the normal force. Okay, so at t equals 4 seconds, if we look back over here, at t equals 4 seconds, we're moving at a constant speed, right? At that point, since we're moving at a constant speed, we know acceleration has to be 0. So, we know acceleration is 0. If we drew a force body diagram, the forces acting on our traveler are Fn and Fg. Okay, those are the only forces. Since the acceleration is 0, we know that Fn minus Fg equals 0, or Fn is equal to Fg. Okay, then since we know the mass of the person, we know that Fg is equal to mg, so Fg is 700, and the apparent weight of the person is just 700 newtons. Okay, so going through this, give yourself 1 point if at some point you wrote down that the acceleration is 0 at 4 seconds. Okay, give yourself 1 point if you knew that Fn was equal to Fg, and 1 point for getting the correct answer. Okay, so once again, part A was worth 4 points in total, part B was worth 3 points in total, and part C was worth 3 points in total as well. So take a moment to just total up your score on the first problem.